This lecture is on dot products of vectors and some of the applications of that, including projections. So first of all, the dot product of two vectors is a scalar, not a vector. And to find the dot product of two vectors, you multiply by component and then you add those products. So if you have u1 comma u2, v1, v2, multiply the first components, multiply the second components, and add those two products. Here are some properties of the dot product. It's commutative, which is not surprising since it involves multiplication and addition. Dot product of 0 with a vector is 0. Dot product of a vector with itself is equal to its magnitude squared. There's a couple other ones here which are of less use. So finding some dot products, here are a few quick examples. 4, 5.23, 4 times 2 plus 5 times 3. 2 comma negative 1 dot 1 comma 2. 2 times 1 plus negative 1 times 2, you get 0. And then here's 0 comma 3 dot 4 negative 2 is another dot product. So again, you get a vector, you get a scalar and not a vector. Okay, going on to example 3, we know that a dot product of a vector with itself is the magnitude squared. So if we're told the dot product of u with itself is 5, what's the magnitude? Well, we can say that magnitude squared is u dot u, which is 5, so the magnitude is rad 5. Okay, now the angle between two vectors. One way to find the angle between two vectors is through this formula here. The cosine of the angle between the two vectors is the dot product u dot v divided by the two magnitudes. And that proof can come about using the law of cosines, but here's the formula we want to use. So here's a sample. We have 4 comma 3 and 3 negative 5, and I draw them 4 comma 3, 3 negative 5, and I do u dot v over magnitude of u, magnitude of v. So 4 times 3 plus 3 times 5 is 27. Square root of 4 squared plus 3 squared is 5. Square root of 3 squared plus 5 squared is rad 34. You take the inverse cosine of that quantity and you get 22.2 degrees. And we can also see that over here. What I've done in this sketch is I've got these two vectors here, their components, and I've calculated the magnitudes, I've found their dot product, and I've done the formula here. I've got the inverse cosine of their dot product divided by the two magnitudes, and you can see that's equal to the measured angle according to Geometer's Sketchpad. So these things do match up. Okay, another thing to notice is that due to our formula for the angle between the two vectors, if the dot product is positive, well, we know the magnitudes will be positive. So if the dot product's positive, this whole quantity is positive, so the cosine of the angle is positive, so therefore it is going to be first quadrant acute. So positive dot product, acute angle. If this is negative dot product, we'll have negative over positive, because again the magnitudes are always positive. So if the cosine is negative, then we know we are second quadrant, so we're obtuse. And finally, if the dot product is 0, inverse cosine of 0 is 90 degrees, so we know that the angles are the angle is right angle, or the vectors are perpendicular, also called orthogonal. And that is the information that we see down here, actually. So two vectors are orthogonal if the dot product is equal to 0. And so this is a bit of a summary of the information that I just mentioned. If you want to find out if vectors are parallel, we'll talk about that a little bit later too. To find out if they're parallel, basically you can check to make sure that the ratios of components are a constant between two vectors. Okay, so here we've got the vector 2 comma negative 3 and the vector 6 comma 4. We find their dot product, we get 0, and so we know that they are orthogonal to each other. Okay, vector components, a very useful idea, especially when we get into physics and you're trying to separate different forces and compare them. And so to do this, we have to talk about the idea of projections. And so we can do the projection of one vector onto another. Here's a couple drawings. I'm going to show you a different one, which I think is a little more illustrative. A lot of arrows on here. Ignore them for a little while. Basically, a projection is imagining that you shine sort of a light from one vector down to another. So if we want to find the projection of vector u onto vector v, imagine shining the light perpendicular to vector v, and the shadow that you see, which is right there, is the projection. And now, if we want to look at the other vector that makes up that vector, here's the other part of vector u. So basically, we have the projection of u onto v, so u projected onto v, we call that the w1 vector, and then w2 is the other vector. And together, these two vectors would add to vector u. As you can see, if we do head to tail, we would end up with this back where we started. And I can look at it the other way, and let me show vector v onto u. So imagine shining the light this way. This is vector v shining onto vector u, and then we look at the w2 vector, and together these two vectors would make it up. And so if we move this around, you can see how the projections change. Okay, so as far as the formula then for projections, the projection formula is over here. So here's our projection formula here. Projection of u on v is u dot v over magnitude of v squared times v. And what I've done is just separated this a little bit. I brought one of these magnitudes out and put it on the bottom. So what you can see is that u dot v over magnitude of v is equal to the magnitude of u times cosine theta. That comes from another formula we have for angle between two vectors. And then I've got v over magnitude of v. Now this blue piece is basically the length of u in the v direction. And then the yellow piece is the unit vector in the v direction. So what this does is it takes that part of u that's going in the v direction and just multiplies with the unit vector there, so it ensures that we get the right length in the correct direction. So that's going to give us the projection, which is the w1 vector. And so for this pair, 2, 3, and 5, 1, here's the dot product, 13 divided by the magnitude of v squared, which is 26, 5 squared plus 1 squared, and then times v, 5, 1. So I distribute the 13 over 26, which is a half. I get 5 halves, 1 half, so that's your w1 vector. Now, because w1 and w2 are going to add up to v, once I know w1, the projection of u on v, or in this case v on u, I can subtract it to get the other vector, the w2 vector. So again, because w1 and w2 are going to add up to vector u, if I want to get w2, I do vector u minus w1. So once I find w1, I'll subtract it from u, which is 2, 3, and I end up with this vector here. So I'm going to go ahead and plot the vectors, and you can see that it makes sense. So we've got 2, 3 here. We have 5, 1. If I imagine shining the light down u onto v, I get this vector, and that looks like around 2.5, 1 half. And then if I go at an angle such to add up to u, this seems like it's around negative 1/2, 2.5. Okay, back over to here. Let's take a look at one more example in the textbook. So here's our formula again. We have vector 3, -5. We want to project it onto vector 6, 2. So here's 3, -5 projected on 6, 2. You see it comes at a right angle. And so we expect to get this as our w1 vector. Okay, so it's always good to see it graphically to get an idea of what's going on. So here's our formula. U dot v is 8. Magnitude of v squared is 40. Times vector v. We get 6/5, 2/5. And 6/5 a little more than 1. 2/5 a little less than a half. So that seems about right. To get w2, I do the vector u minus the vector w1, and I would get 9/5, negative 27/5, and that would be down here approximately. Or actually, well, they just put it parallel, but usually you'd have it coming from 0, 0 in component form. Okay, a few more sample problems. This is some sample dot products, 4, 10 dot -3, 1, so 4 times -3 plus 10 times 1. So these vectors have a negative dot product. They would be at an obtuse angle to each other if we went that far with it. 2 times 9 plus 5 times -3, we get 3. These would be at an acute angle. Over here, we want to find the angle between these two vectors. And so here's our formula for angle between two vectors. Dot product up here, magnitude of u, magnitude of v, 27 over 5 right at 34. And here it is, 22.17 degrees. I think this was the one in the book also. And we can, here's on the calculator how it would appear. Idea here is to find out whether these vectors are parallel, orthogonal, or neither. Well, if you have 4, -6 and 3, -2 and you do a dot product, you'll end up getting 0, and therefore they are orthogonal. If we have 4, 14 and the vector 6, 21, so basically the given information was 4, 14 and 6, 21. If you multiply each component here by 3 halves, basically you get this new vector. So the idea is you can take a scalar multiple and multiply it by one vector to get the other, and therefore they're parallel. Or another way to look at it is 6 divided by 4 is equal to 21 divided by 14. And finally, one more projection problem. We're going to project 4, negative 2 onto 10, comma 2. So here's our projection formula. Dot product 4 times 10 plus 2 times negative 2, magnitude of v squared times v. And there's our projection to get the W2 vector. You do u minus your projection W1, and we do one vector minus the other, and there we go.